A simple pendulum consists of a mass and a string, with the string suspending the mass from some fixed point. So we have some mass, which we'll call M, and we have a string of length L. The pendulum has a natural equilibrium position where it hangs straight down, and the displacement of the pendulum from the equilibrium position is going to be represented by its coordinate x along a line from left to right. And this model applies if x is much less than L. That is, the displacement from equilibrium is much less than the length of the pendulum. In this case, we have the weight of the pendulum, which is mg, acting straight down, and we have tension in the string acting on the mass with a force that we'll call T. If x is small, then the vertical component of the tension vector T is not much different than the magnitude of the tension, and if x is small, the motion of the pendulum will be almost all in the horizontal direction. Since the motion is almost all in the horizontal direction, it follows that the vertical component of the tension and the mg are pretty much equal and opposite, meaning that the tension is pretty close to mg, from which it follows that a vector diagram with the tension here and the x component of the tension here is geometrically similar to the triangle formed by the pendulum and its horizontal displacement, so that Tx is going to equal mg over L times x. Now I'm skipping some details here. These details will be familiar to any student who's had a physics course. But the result then is that for a freely swinging pendulum, the x component of the tension is the net force. So we have the net force equals negative mg over L times x. The negative sign indicating that the tension is in the direction opposite the displacement x, so that if x is positive, the tension is pushing to the left. If x is negative, the tension is pushing to the right. Now we know that the net force is just mass times acceleration, which is mass times the second derivative of x, giving us a differential equation, mx double prime equals negative mg over L times x. Dividing both sides by m, we have x double prime equals negative g over L times x. This is a differential equation that we easily solve by the methods we've developed. We let x, we assume form for x being a e to the kt, so that x double prime equals k squared AE to the KT. Substituting into the equation, we have K squared AE to the KT equals negative G over L AE to the KT. Dividing the AE to the KT, we have K squared equals negative G over L, so that K equals plus or minus the square root of G over L times our imaginary number I. We can see that when this value of K is substituted back into the form of our trial function, we're going to be on familiar ground with e to some multiple of I, and we'll continue with that in the next clip.